Welcome to 2.6. Okay, this section should be easier than the last section, which is why the last section I usually split up to make things a little bit more manageable. This section should be relatively straightforward, I'm hoping. And it's kind of fun, and I think it's a lot easier to visualize, which is useful. So again, I think I mentioned these at the start of the chapter 2. One of the cool applications of integrals is like centers of mass. We can do quite a bit with a single integral, and even more when we add multiple integrals. This is, one of the explanations for something like this. Cool little party trick. You can actually balance a fork and a spoon on a toothpick at the end of a glass because the center of mass of this system, the system being the toothpick, fork, and spoon, that center of mass is actually right here. Even though there is no mass right there, right? There is equal weight to the left and to the right of the toothpick. And there's equal weight above this point and below this point. So that makes this the center of mass, which means this doesn't tip any of the directions because that's where it's centered. And then again, something I've also been really into recently is rock climbing, and center of mass is huge for rock climbing as well. There's a technique called flagging, which is why this guy's left leg is just out here. There's no foothold or anything, and there's a lot of reasons why someone might flag. And one of them is just getting a body part over to the left moves your center of mass over to the left. And there's a lot of reasons why you might want to do that in rock climbing. All right, always have to be aware of where's your center of mass. That can make certain things much easier or harder, depending on what you're doing. So that's what we're talking about in this section, and it's pretty cool, I think. Of course, we're not doing any super complicated stuff until later, but we're giving ourselves the tools to talk about fun stuff. And there's a cool little project that may or may not appear as an activity. But I get ahead of myself because I get excited. But I like getting excited about math. Also, another musical comment. There's a song called "This Is the Moment" from the Jekyll and Hyde musical. There's probably other songs about moments, but if you like musicals, it's an okay one. Kind of cheesy, kind of silly, but kind of cool. I used to really like it. I used to listen to a lot of musicals. Anyway, so let us look at a seesaw. Another picture for you. Nope, not that. So, I think we've all kind of been there. This is how this first video is going to start. Right? If you're on the playground, well, maybe we haven't. Maybe only old people played on seesaws. I don't know. But if someone's heavier, they're going to sink down. But if the heavier person moves a little closer to the inside, there's less force on that side because the force is proportional to how far you are from the fulcrum. The farther you are from this balance point, the bigger the force that, I don't know all the fancy physics words, but essentially the bigger the force that is being applied. Again, I'm sure I messed up the words, but that's the idea. The farther out you are, the more it's getting tilted. And we're going to be kind of thinking about that backwards. So let's introduce this with some nice pictures. So let's look at a seesaw. Not really a seesaw, but we can call it a seesaw. And let's say that there's one mass over here, which we'll call mass 1. And there's another mass over here, a different size maybe, that we'll call a second mass. And it turns out that the middle of this is when this equation is satisfied. The center of mass is the location, so that this is satisfied where distance is just the distance to the center. So again, maybe the center is right here or something. We can call that center a location x bar. So again, this is our first distance, d1. And this is our second distance, d2. So we can use this fun little fact. Again, it's proportional to the distance. We can use this fun little fact to say, well, how can we find where x bar is? How can we find this location, the location of this fulcrum, so that this system is balanced? So what we're going to do is kind of flip this on its head. So distance 1, let's think about these as x and y coordinates. All right, let's say the origin is somewhere. It doesn't matter where the origin is. Let's say x equals 0 is somewhere. Doesn't matter where this x equals 0 is at all. Doesn't matter where that x equals 0 is. Well, then distance 1 is just the distance between x bar and x1. Again, we can call this x1. Ooh, also, I made this small mistake. Actually, it's kind of a big mistake. My diagram has the wrong distances. We should be thinking about these as point masses. I'm drawing them as two-dimensional, but really we're thinking them as point masses where the mass is like on a point. Now that works for three-dimensional and two-dimensional masses, but then we have to draw it towards its center of mass, which is kind of self-referential. But the picture should really be drawing the distances is the distance to the center of these masses. Okay, so likewise, this right here is going to be x2. So m2 stays the same. And again, what is d2? Well, it's the distance between this and that. x2 is going to be bigger. We'll have x2 minus x bar. Again, we have them in different orders because we always take bigger minus smaller. And it doesn't matter where x equals 0 is. Maybe this is x equals 0. X bar is always bigger than x1 in this situation. And there's some other ways of phrasing this as well. So all we need to do to find the center of mass, that's it. Solve this equation of a line. This is a linear equation in terms of x bar. We're solving it for x bar. So good practice right now. Pause the video, try to solve for it, and then unpause the video and see if we get to the same thing. That's your formula for the center of mass. That's your formula for this video. So we're going to have to distribute on both sides. We're going to get m1 x bar minus m1 x1 equals m2 x2 minus m2 x bar. There's a lot of letters, but all that matters to you and me is that everything with an x bar needs to be on one side. This is a linear equation. If it's got an x bar, get it on the left. If it doesn't, get it on the right. That'll give us m1 x bar plus m2 x bar. And the right side is going to be m1 x1 plus m2 x2. Now we can factor out an x bar. I just want to show that, again, if you factor out an x bar, you're left with m1 plus m2, but I don't want to write this whole step out. We're dividing both sides of this equation by m1 plus m2, which leaves us with something very nicely symmetric. m1 x1 plus m2 x2 divided by m1 plus m2 is our center of mass. Again, no cancellation here. You can only cancel when things are factored. That's kind of cool. So what is the top of this? What is the bottom here? The top is what's known as the first moment of the system. Think of it kind of like a weighted average. If you remember like probability or statistics, expected value, the probability times the x value, this is kind of what's going on here. And a lot of times in this book, we'll just get rid of the word first and just say the moment of the system. There are second and third moments. First moment is kind of like an expected value. Second moment's kind of like your variance. And again, moments in general for physics, statistics, measure theory, all sorts of math applications have this concept of moments. And those different moments do mean different things. But here in this book, we're really only talking about the first moment. So we'll often abbreviate it and just say the moment of the system. Well, what's our denominator here? That's just the total mass. Right? So it's both people on the seesaw. And again, in this case, we're not thinking about the mass of the seesaw, only the objects. But when you say total mass of the system, we are not including the seesaw. All right, I have notes here. I think I've pretty much talked about what I want to talk about. Let's summarize this in a theorem, and then that'll be this video. Theorem 2.9, center of mass. I'll often abbreviate that COM of objects on a line. So again, visually, I'm thinking about this in 2 dimensions. But mathematically, what we're doing here is in 1 dimension. We'll do 2 dimensions 2 videos from now. So this theorem says that if M, let M be the total mass of n objects. Because of course, there can be more than 2 people on the seesaw. And all the calculations we did are exactly the same if there are n people on the seesaw. We can fit a lot of people on this seesaw. All right? It all holds. And so let's just stretch this out. So what do you think is going to happen, right? If this is the center of mass formula for 2 things, what do you think the center of mass formula is going to be for 3 or 4? Hopefully, you know where this is going. Hopefully, you have a guess. We'll see if your guess is right. The M is the total mass of n objects on a line. The moment, or first moment, of the system with respect to the origin. That's important. Now, I said it doesn't matter where the origin is for finding the center of mass, because physically, it doesn't matter where we call the origin. But this number that we get at the end will absolutely depend on the origin. These distances, these x-coordinates, depend on where we call the origin. So the moment with respect to the origin, because if the origin's in one place, our moment is a number. It'll be one value, but if the origin's somewhere else, the moment will be a different value. The center of mass will be in a different place relative to the origin, but physically it will always be in the same place, right? Whether this is x equals 0 or this is x equals 0, doesn't matter. This will still be the center of mass, our fulcrum. Okay, so the moment of the system with respect to the origin is given by capital M. And it's, we got sigma notation. The sum from I goes from 1 all the way to n of m sub I, x sub I. Which again, is exactly this. We're just summing up all the m sub I, x sub i's. It just so happens that when there's only 2, we're only summing 2 pairs. But we're actually summing n pairs if there are n objects. And the center of mass of the system is x bar. Well, what's the center of mass? It's the first moment divided by the total mass. So first moment, capital M, divided by total mass, little m. I could box this whole page, I guess. That's important. Okay. And this is really the crux of the entire section. When we get into higher dimensions, it'll look a little bit more complicated, but this is really the same thing. We're just expanding on it. Let me know if you have any questions. Good luck. Bye-bye.